Okay, welcome everybody. Today we have a very busy day. We have 3 presentations today. 2 of them about simulation and 1 of them about the mission concept. So today we will start with Elke Roediger, who's visiting us for a month from the University of Hamburg, and she will tell us about shaken or stirred but mixed fluid flow experiments in the ICM. Then we will continue with Lorenzo Sironi, who is working in CFA, and Lorenzo will tell us about magnetic reconnection in relativistic astrophysical jets. And finally, we will hear from Randall Smith, who will tell us about the Arcus mission concept, exploring the formation and evolution of clusters, galaxies, and stars. Elke, please.
Thank you. Is the microphone on? Can you hear me?
Yeah.
Okay, good. So today I want to show you how to do fluid flow experiments in galaxy clusters, or how to use gas-stripped elliptical galaxies and clusters as probes for the effective viscosity of the intracluster medium. And the issue, of course, is that we still don't quite know what the effective transport coefficients, that's thermal conductivity and viscosity, are in the ICM. And the difficulty lies in the complexity of the interactions between the charged particles in the ICM and the magnetic fields in the ICM. And in very short, the story goes like this. The ICM is a fully ionized plasma, and if it was not magnetized, you can sit down and work out the mean free path, and it turns out to be pretty long. I plugged in some typical numbers here, and it's strongly dependent on the temperature, and we get numbers around a few kiloparsec. And that reaches the size of galaxies. That is a concern even for the fact or the question whether we can use any hydrodynamic treatment at all. The mean free path is also linked to the viscosity and thermal conductivity, so if that's large, these 2 coefficients are large. However, the magnetic fields exist in the ICM, and even weak magnetic fields would dramatically decrease the mean free path perpendicular to the magnetic fields. So if we have mostly ordered magnetic fields, we might end up with anisotropic transport coefficients, so anisotropic thermal conductivity and viscosity. However, we don't quite know what the magnetic fields actually look like. They might be tangled more, and the direction of reduction of mean free path might change quickly. And if all we are interested in the end, is an average over boxes inside which the direction changes, we might end up with an effectively isotropically reduced thermal conductivity and viscosity. There are people working on this from the plasma physics point of view, trying to work this out theoretically, and it turns out to be pretty hard. Whatever their results will be, at the end we need to confront the observations, and we wanted to do part of that step by taking an empirical approach and trying to empirically measure the effective viscosity, in this case, of the ICM. So the idea is pretty simple. Imagine we could make a fluid flow experiment. Imagine we could take some object and drop it into a galaxy cluster and watch the ICM flow around this object. These here are some photos from an old book where, I think in this case, cylinders have been exposed to a flow around them, and the wake of these cylinders depends strongly on the viscosity of the fluid that's flowing around them. At a low viscosity, we get a turbulent wake, so we get mixing in that wake, and it looks very different from what the wake would be like at high viscosity. Then we get the laminar flow around the object, and we don't get a lot of turbulence in the wake at all. So if we could do something like that in galaxy clusters and see that wake, we might make the measurement and distinguish what the ICM behaves like. So the good thing is, nature is doing these experiments for us. Elliptical galaxies are flying through the galaxy clusters and are experiencing the ICM as a headwind towards them. So it's pretty much the same situation. It's even a bit nicer because the gaseous atmosphere of these galaxies gets stripped while the galaxies move through the ICM, so it will end up in the wake somehow, and will make the wake hopefully brighter and visible for us, so that's how we can observe it. And that's the idea of what we try to do. So we have the good observations, and we want to look at the wake and see what it is like to make the distinction. We have to be very careful in making this analogy, though, because in these simple cases here, in these laboratory experiments, there are quite some assumptions that went into there that are certainly not true for galaxies and clusters. to name just a few, in these laboratory experiments, the upstream flow is a steady flow, so it has constant density, constant velocity. And the objects are solid objects. They don't change in size, and the standard example is a sphere or a cylinder, so something round. And certainly none of this is really true here. And there are many interesting aspects in making this analogy and making it work, and it does work if we do it right. But the one I want to talk about today is what we need to do to get the anatomy of the flow around the galaxy right. So the anatomy, what I mean by that is the structure here. So it's easy for the laboratory experiment. We have an upstream flow region, then we have the body itself that poses an obstacle to the flow, and downstream of that we have the wake. Now we need to figure out these regions for the case of the galaxy. It's pretty obvious for the upstream region, that's upstream of the galaxy. But what's the tricky part is, what is actually what we see here? Is that still part of the body that poses the obstacle to the flow, or is that already the wake? And if you think about it carefully, we could work it out without doing anything like simulations, but it's much nicer to see when I show you a simulation. So that's the sort of simulation I've been doing here. I've been running a hydrodynamic simulation that was specifically tailored to that galaxy I've been showing all the time, M89 and Virgo. And that means I've included a potential for the galaxy that mimics the potential of that specific galaxy, as we can see it from the stars, and derived from what dark matter it likely has, and also in terms of the orbit it's going through the Virgo cluster. So the simulations are run in the rest frame of the galaxy, so it has a headwind coming towards it, and that headwind changes as it would for the galaxy moving through the cluster. So it gets denser and faster with time. And the whole thing then looks like this. So this is a density slice through the simulation box, and the simulation starts at almost 1.5 megaparsec away from pericenter. I'll just set it going so that you can see what's going on, and keep an eye out on that region that I marked there. So we see how the stripping proceeds in a very specific way. The upstream part of the atmosphere is pushed back. Gas removal occurs mostly along the sides via Kelvin-Helmholtz instabilities here. But if you keep an eye on the downstream part of the atmosphere, there isn't too much going on. For a long, long time, the galaxy can retain a lot of its downstream atmosphere. That's pericenter already. I've run the simulation further. It takes another 400 mega years before that downstream part of the atmosphere is lost. The reason is pretty simple. The front part shades the downstream part. So the galaxy can retain its downstream part, and that's the whole thing we see there is the body, what poses the obstacle to the flow of the ICM. So we can go back to this picture now. The upstream region, we had already identified that before. And this whole part of the galaxy, its remaining atmosphere, poses the obstacle to the flow. And the wake comes only downstream of that. So keeping that in mind, we can now go back to the observations and first turn the simulation into a mock observation, how that would look like in X-rays. That would be about like that. And what we've just seen is that that whole region is the obstacle, it's not the wake. Well, it does look a lot like a tail. So what I would propose to do is call this thing the remnant tail, which indicates it's just part of the atmosphere, it's not stripped gas. That looks very much like what we saw in M89. So that tail of M89 is very likely just the downstream atmosphere that has been sitting there all the time. It's not stripped gas. That's important because we wanted to look at the viscosity, and for that we need to look at the wake and not at any part of the actual body. So the wake is only downstream of the remnant tail. And it gets interesting when we now run the same experiment and the same simulation with viscosity. So I've included here an isotropic viscosity at just 10% of the nominal Spitzer value. And the near part of that whole long tail looks pretty similar whether or not we have viscosity, which is simply because that's the downstream part of the atmosphere that has been the same in both cases. They look very different when we look at the wake, which is just what we expected from the analogy with these spheres or cylinders in the flow. At a considerable viscosity, viscosity prevents the mixing between the denser and cooler stripped gas and the ambient ICM. That's why we can see this wake and not the other one. Well, the Chandra image here doesn't cover the wake. It just covers the remnant tail. And the only observation that does cover the wake is XMM, but it's very shallow. So we've looked at the numbers, and we'll do it again, but our verdict right now is if we had if the ICM had a viscosity that's effectively isotropic and close to the Spitzer value, we should see that wake in this image, and we don't. So that indicates that we can exclude an effective isotropic viscosity for the ICM that's as high as Spitzer or close to it. It's a very short outlook. We have more data than just one galaxy. We have even more examples than what are shown here, and we've started doing work on NGC 1404 in the Fornax cluster, and also some simulations on a galaxy similar to M86. So if you want to know more about this, please ask me. And as a summary, I put up that slide again with the main message. Thank you very much.
Thank you. Questions? Yes.
What sort of Mach number is this?
It starts from 0.5-ish and goes to 1.5 near pericenter.
Is the analogy actually good enough that you can measure the viscosity? If you were suggesting something like that at the beginning.
If we do it right and look at the wake, yes. To get a precise number, we need to get the dynamics of the situation right. Which is why we started with M89, because it looks reasonably simple in terms of that it's gone a long way into the cluster already. It's not still sitting on the outside. It even looks like it has an almost roundish potential and is not elliptical. So we would be, yes, sneaking our way in and excluding cases on both sides.
Do you have a stellar source term in the galaxies? Are you looking at all?
I haven't. I had a look that for just one infall, it shouldn't matter. So the rate of gas injection is not high enough that it should change the story considerably.
What are the temperatures that are corresponding to galaxies?
The galactic gas is at about 0.4 keV, and the Virgo ICM, if it's not shocked, is at 2.4 keV.
So I suggest Lorenzo is going to give you the speech, and then we have time for one or two speakers.
Is there any reason why Sironi from Walsh observations were excluded from the analysis of LA tonight?
Why it was excluded?
Yeah.
And
We showed only PN observations.
that was we can look at the other ones too. That was what the observing experts deemed as the most reasonable to look at first. So we'll try to combine it, but we need to go deeper to make a real difference.
Any last question?
I don't know, maybe more a question for Ralph than me. Do you see anything in the X-ray spectra? Because if this is atmosphere that comes back from the galaxy,
Yeah.
I would see metallic, respective to metallic.
Okay, so the tail is actually a little bit warmer
Wait, I
than
need to put my hand.
the core.
Oh, sorry.
So you gotta be a little bit careful. The reach tail, the remnant tail, the right part of the tail. Okay, it's actually a little bit warmer. The core part of the gas is about 500 degrees. And then it gets progressively hotter, about 600, 700, 750 degrees of the tail. And that region where it looks like the surface brightness drops a little bit and the tail flares, which you actually see the weight. Okay, that is also about 800 dB. The statistics there aren't really good enough to get abundance alterations that we need. So we looked at that carefully, and it just isn't really right enough to do more than have the temperature in two regions and then get the abundances. In the core, we can actually constrain the abundances very well, but not in the tail. It's essentially like too low surface brightness. The background is not a negligible subtraction, and it limits the signal to us.
Okay, thank you very much, Elke. See you at everybody.
Very good. So I guess this accounts for talk simulation number 2, but I would really try to emphasize the connection with the observations and the fact that we can start from first principles on a model that is based from ab initio calculations and then have meaningful and very constraining prediction for the observations. The context is reconnection in blazar jets, jets from active galactic nuclei that are emitting along the line of sight. And there are 3 properties of blazar jets that I would like to focus your attention on. And are quite general for all blazars. First of all, blazars are efficient emitters. About 10% of the power of blazars comes out as radiation. Here is radiative power versus jet power, and the line here is about 10% of total jet power going into radiation. Second thing, we generally see rough energy equipartition between the emitting particles, electrons, and the magnetic fields. As you can see here, it's about same power in magnetic energy and in energy of the emitting electrons. And finally, we require very broad non-thermal particle distributions. And very often these distributions are hard. And by hard, I mean that the number of particles differential in energy or in Lorentz factor goes like Lorentz factor to the minus p, where the slope p is sometimes less than 2. So very hard spectra, which are required to explain the very hard GV, TeV observations. This stopped working, so I'll just point. And the picture that we have in mind as the mechanism that is responsible for the generation of photons, or better, the generation of particles that will emit the radiation that we see, is magnetic reconnection. And the situation that I'm envisioning is a situation in which there are loops inside the jet with a given polarity below this region and the opposite polarity above this region, and you have a configuration in between, which is depicted here on the right, in which the field lines are having a different orientation on microscopic plasma scales. You'll clearly see the shape, which is a reminder of typical pizza slice here. That's why I'm talking about it here. The physics is that you have field lines of opposite polarity that are converging to a central point that is called X point. And the motion of the field lines into this region is causing the presence of an electric field, just the V cross B electric field. So there is potential from this electric field to accelerate particles. The regime of reconnection that I'm interested in is the so-called relativistic reconnection regime, in which the magnetic energy is larger than the rest mass energy of the particles. And this is a configuration that is realistic for blazar jets. Alternatively, the Alphen speed is roughly equal to the speed of light. And the key question that we are trying to address is whether reconnection in such systems is capable of generating the non-thermal particles and explaining the radiative signatures that we see. And in order to do this, we resort to first principles methods. The particle in cell method is a very fundamental method of plasma physics. It basically relies only on Maxwell's equations and the Lorentz force. The particles are moved by the Lorentz force. They deposit their currents on the grid. On the grid, we solve for Maxwell's equations, and the electromagnetic fields are used to push the particles around. So nothing more fundamental than that. On the other hand, the simulations are often constrained to small scales, so one needs to do a careful extrapolation to the astrophysically relevant scales. So let me give you a description of how reconnection looks like. We start with a magnetic field that is oriented to the left in the top part and to the right in the bottom part. And we let the system evolve, and this is how it evolves. It starts with the formation of small-scale islands, which then grow and coalesce to larger and larger scales. And at the same time, you have the constant formation of small-scale islands inside this under-dense region. You see the process is definitely unsteady, and it's hierarchical. You have big islands and then islands on a smaller and smaller and smaller scales. The other interesting thing from this plot is that if you plot the magnetic minus electric energy, you see that there are regions which are in blue and green here where the electric energy or the electric field can actually be larger than the magnetic field. So these are regions which are very promising for particle acceleration, and that's what reconnection gives you from first principles. Another important ingredient of this story is the inflow and outflow speed. The inflow speed is the speed at which the magnetic field is being dissipated into the reconnection region. That's about 0.1 of the speed of light for typical parameters, so trans-relativistic inflow speeds. The outflow speed away from this central X point is often ultra-relativistic, approaching the Alfvén velocity, which, as I said, for this configuration is very close to the speed of light. The basic question that we started from is this configuration capable of accelerating non-thermal particles? And the answer is yes. If you measure the spectrum from the reconnection region, you find that it's not consistent with a Maxwellian, but it's rather similar to a power law with an index for a power law equal to 2. Over time, the normalization increases just because more and more particles are advected into the current sheet. And the maximum energy also increases with time. We can measure how fast this goes, and it goes linear with time, which is very promising for accelerating particles at a fast rate. The rate of particle acceleration is proportional to the speed at which the highest energy evolves is related to the inflow speed into the reconnection region. But the important thing is that this goes linearly with time. So it's promising for fast acceleration in a relatively short time. This was based on 2D calculations. The 3D physics might be different because in addition to the mode that I described so far that will create magnetic islands in this plane, there is a competing mode which is called drift kink, which is expected to kink the current sheet in the other plane. And what you see is indeed that the drift kink dominates at early times, kinking the current sheet, but at later times, if you let it evolve for longer, as you should expect, because these are simulations that are only limited to small scales, you see that you totally forget about the drift kink. You see the formation of big islands. The merging of the islands proceed the same way as in 2D, and you even have the formation of the small-scale islands here, which are actually flux ropes in this direction, which are reminiscent of the small-scale islands that we were seeing beforehand in the 2D simulations, in between the big islands. So the 3D physics is similar to 2D. You shouldn't worry about 2D for reconnection versus 3D. This is the spectrum from the 3D simulation. Over time, it increases its maximum energy. The slope is a little bit steeper than the result from 2D. As I said, from 2D, you have a slope around 2. This is 2.3. But the qualitative behavior is very similar. And once again, the maximum energy increases linearly with time. The only quantitative difference is that the rate at which you're dissipating the magnetic energy in 3D is about 0.02 of the speed of light as compared to 0.1 that you have in 2D. So in some sense, the process is less efficient in 3D, less fast, but qualitatively looks really very similar. So I just want to spend one slide on the details of the acceleration process by following one representative particle here that will interact with the current sheet. And on the top panel, I show the energy of the particle as a function of time as it interacts with the current sheet. And you see that there is a critical time in which the particle energy starts to go up. And this is now. That's when the particle interacts with the X point. The region that is special because the electric field can be larger than the magnetic field, so the particle can be readily accelerated. This is the first acceleration episode. And then the particle is trapped inside these big islands. Pretty much nothing happens in its energy up to the point in which these two islands are merging. The particle is trapped in between, and it's bouncing off the two islands. This is the same physics as the so-called Fermi process that you have in shocks, in which you have a convergent flow, and a particle that is scattered in between the two converging flows will see its energy going up. So a two-stage process for acceleration of particles in reconnection. The first one in the interaction with the current sheet, the second one as the particle bounces in between two magnetic islands. This is as far as I wanted to go for the mechanics of reconnection. And now let me get to the implications. So as I said, blazars are efficient emitters. About 10% of the energy, or 10% of the power of the jet is supposed to go into radiation. And we can estimate the efficiency of reconnection by measuring how much energy is in the electrons, which are willing to radiate the energy in the fast cooling regime, versus the total energy balance of the flow. And you can see that this is up to 50% for the electron-positron jet and around 20% for an electron-proton jet. You can make it lower by changing one more parameter that I haven't talked about, but feel free to ask about that. you cannot make it higher. So in some sense, the 10% that is inferred from the observations is well within the regime that reconnection can capture. The second property is the equipartition of the particles and the magnetic energy. And you remember that they are roughly in equipartition, so the ratio between the energy in the electrons and the energy in the magnetic field should be around unity. Here we compute the electron energy divided by the sum of the two, so this should be around 1/2, and it's about 0.7 for the electron-positron case, it's about 0.6 for the electron-proton case. So once again, reconnection can naturally account for another property of Blazer emission. And finally, since my time is also over, as regard to the possibility of producing extended distributions with a power law shape, sometimes even harder, with a spectral index that is harder than 2, reconnection does naturally produce that. This has been confirmed by 3 independent groups in the last year. The slope is steep if the magnetization is smallish, around 1, so equal amount of energy in magnetic field and in the rest mass. And the slope is harder as you go to higher magnetization. So for a slope to be harder than 2, you need to think about magnetizations that are higher or of order of 10. And this concludes my investigation, and I will just leave up my summary, asking for your feedback and your questions. Thank you.
So, questions, please. Yes.
In your simulations, do you keep the magnetic field constant or you couple them to the gas?
So this is done totally self-consistently, which means that the only thing that I provide is a description of what the configuration is at time equals 0.
Okay, so just initial conditions.
Yeah, and then everything that happens after that is due to the interplay between the electromagnetic fields and the particles. So for example, what happens is that there is a region, which is the X point, in which the ideally you would like to have a current that is capable to sustain the curl of the magnetic field, but in reality the particles that you have there are not enough to sustain the current, so the magnetic field has to change its topology, and that's what reconnection is. But this is entirely self-consistent within the simulation.
Thank you.
Right.
So you showed that the gamma was basically, the Lorentz factor was going up linear with time, but initially not. Is that where it goes up linear? Is that where it starts bouncing? That point?
That is a very good point. The initial growth is actually just a wait time, if you want. We can look at it 2D. Oh, sorry. This initial phase is a quiescent phase. So reconnection doesn't start immediately. It needs a few light crossing time across the current sheet to know about the thickness of the current sheet. So basically there is no dissipation here. And then there is an explosive phase. And the linear phase is indeed when the islands start to merge and the Fermi process starts operating between the merging islands.
Yes.
Is there a regime where, say, the Lundquist number isn't quite high enough to give you the tearing mode, but you still have the drift kink mode?
These simulations are resolving the tearing mode. So it's a question of what is the critical length of the current sheet such that you will see the tearing mode. In 2D, it's very clear that you have a minimum length scale. And if you stretch the current sheet more than that, then you start breaking it into a second generation of islands. That's called secondary tearing mode. What happens in 3D is that the competition is actually on different planes. So it's kind of an unfair comparison to do. The question is which mode grows the fastest. And the fastest is the drift kink. But the effect of the drift kink is only to increase the thickness of your current sheet a little bit. And then the secular tearing mode wins at later times. So it's just the tearing mode at that point grows on a current sheet that is slightly thicker than what you started from. But the tearing mode is there, and that's what gives the particle acceleration. It's been known since 10 years ago in this business that the drift kink itself only gives heat, no non-thermal particle acceleration. And that's why people were worried about 3D, because in 3D the drift kink grows faster, so you might end up just having heat and not particle acceleration. But what this shows is that if you evolve it to late enough times, then the tearing mode wins anyway. Eric had a question, I think? No.
Okay, I think we have to move on.
Okay.
So last time Lorenzo wants to.
This is not working very well. But. Oops, I might have broken something. If you put it in your pocket.
Pocket's good enough. Okay. Hopefully this is working. Looks promising. Oh, broke it badly. That's right. So there we see the cosmic microwave background. Much better. Okay. Hopefully. Come on, you can do it. There we go. Okay. Sorry about the resolution here. Somehow it got degraded. But I'm going to talk to you today about the Arcus mission. Arcus is a new X-ray grading spectroscopy proposal. And unlike most missions, it's not actually an acronym. Arcus is actually the Roman name for bow or even rainbow, chosen by Mike Novak, actually, who's in the audience. And you can see it's a large team of organizations and people. It was led here out of CFA, but involves a large number of teams internationally. So here's the basic facts. It's proposed in the 2014 NASA AO, went in on December 18th. I went to sleep and then woke up again sometime in January at that point. It will be installed on the International Space Station if we're selected, hopefully by the end of 2020. That might sound like it's a long way away, but trust me, it seems to me to be tomorrow from the point of view of getting everything done that would need to be done. This is about as fast as you can possibly build anything to do that's going to go up in space. Here's our basic science outline. I'm going to go into a bit more detail of each one of these. But for those of you who just want to, the just the facts approach, the bandpass is 9 to 51 angstroms. This is set both by our technology and by our mirrors. For those of you who like to think in energies, I suggest if you want to use grading spectroscopy, you start thinking in angstroms. But if you still are there, this is the basic bandpass. We're shooting for a resolution greater than 2,000 overall range around this. It turns out, for various fairly straightforward technical reasons, it's hard to make a grading spectroscopy with a constant energy or constant resolution in across the entire bandpass. So what we've done is chosen to maximize it right here around where the oxygen lines are. So this is our primary goal. Effective area is more than 400 square centimeters in this bandpass, more than about 200 most everywhere else. And for those of you who are visual thinkers, here is a spectroscopy figure of merit. Now, this is a bit messy because it's the figure of merit measured by the resolution times the effective area to the 1/2 power. This is relative to the best current spectrometer, i.e. whether or not in this units XMM RGS is better or Chandra LETG or HETG is better. So that's what we're comparing to. The point you're supposed to get out of this is a factor of 10 increase, right about there. And so pretty much across the bandpass, we're at least a factor of 10 increase in figure of merit. At our key bandpass, it's more like 25 to up to basically 25 up to 30. And you can see there are lots of very strong lines in this bandpass. We're not going to be short of lines. So where is this thing going to go exactly? And what's it made of? Well, it's using grazing incidence silicon pore optics. Now, if you've heard the phrase silicon pore optics before, it's probably in connection with the Europeans. It's a group in the Netherlands that's making this called Cosine Research. It's a new technique for making mirrors, and it's the one that's going to be used for the Athena mission in Europe that will be launching in 2028. So we are essentially piggybacking off of the fact that the Europeans are putting in many hundreds of millions of euros into developing these mirrors. They need many hundreds of these mirrors. We need about 75. They will be developing techniques for making them very fast, very cheaply. We are simply going to be sitting around taking advantage of all of those effects. It will use the International Space Station as an observing platform. This gives us some huge number of benefits. It means, for example, that instead of having to build a telemetry system, we simply have to have an Ethernet system. It means that instead of having to have solar panels, we simply have to have a power plug that plugs into the space station. It has disadvantages. Working with the International Space Station, it should be kept in mind that this is a $125 million proposal. The International Space Station folks spend $125 million every time they send groceries up to feed the astronauts. So we are not exactly driving their considerations because we're relatively small potatoes compared to their $125 billion satellite that they're operating. That said, they do provide a huge number of benefits. We also get a nice launch up in a SpaceX Dragon trunk and robotic installation right onto there. This, by the way, just to give you an overview of where we are, this would be about where we'd be sitting. If you're familiar with the NASA's NICER mission, it's sitting right about there as well. The AMS is sitting right there. You might think that you'd get great visibility from a position here or here, but it's important to remember that these solar panels actually move. So actually, we will never be looking in this direction. We'd always be looking up this way. And oh, by the way, one of the other benefits, and yes, you are in low Earth orbit, and so you have low background because you're protected by the Earth's magnetic fields. Tragically, however, there's a Soyuz sitting right there, which has a very powerful radioactive source, because that's how the Soviets designed their reentry mechanism. So it's how they look for reflections of their hard X-ray source reflecting off the ground in order to know when to fire the retro boosters in order to do a soft landing. Tragically, however, they cannot turn off their hard X-ray source. So it's sitting there increasing your background. Fortunately, it's giving you mostly hard X-ray, very high energy detections in our detectors. Since we're a soft X-ray mission, we have an easier time filtering them out. This is actually a big problem for NICER, or would be, except for the fact that they've got AMS in the way, which is acting as a lead shield for them. Don't tell Ting. So what are our goals? We're looking for structure formation. We know that only about 15% of the mass in the universe is normal, and the rest of it is dark matter or dark energy or something else. But even that 15% we have trouble finding. We know that most of it is beyond the virial radius of galaxies and clusters, but we don't know how it got there. Did it start out there and then galaxies and clusters formed? Did galaxies and clusters blow that material out after formation? Is it a combination of the two? It's important to realize that this isn't a problem just way out there. We don't even know really what's going on in our own galactic halo or local group. So we would definitely like to have a better grip on where is all that stuff out there in the universe. So how are we going to do this? Well, so here is a quasar at a redshift of 0.2, so it's reasonably nearby. And here are a couple of galaxies that just so happen to be in the field of view, plus some other stuff. But these are our 4 galaxies of particular interest here. Notice that they are all, this is critically important, and that they're at lower redshifts than this one. You can probably guess what's coming next. So now you can look at, for example, for each one of these galaxies, what the projected radius of this galaxy is relative to the AGN that we're looking at. So for example, this is a fairly nearby galaxy. This is 235 radial distance projected on the sky for this particular source, 308, 156. So basically, each one of these galaxies gives us a different distance, radial distance, on the sky. Well, let's imagine we observe this source. We're going to look at it for a long time, 500 kiloseconds. We assumed a moderate brightness for the AGN, typical spectrum. And here's what we'll see. We'll see a strong oxygen 7 line from the Milky Way halo. We'll see a oxygen edge from our own Galaxies ISM, but we will also see bing, 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 and bing oxygen lines from the halos of those 4 galaxies. And what can we do with those oxygen lines, since we now can measure their, for example, equivalent widths, is stack them all up on a plot of galactocentric radius versus the oxygen 7 equivalent width, and compare it to, for example, a beta model with 1/2 versus, say, an NFW model that would look like this. And you can see that we can fairly easily tell the difference between those two models and get a grip on where exactly these two different, where the oxygen that 7 that we're seeing is coming from. So you might be familiar, for example, with grading spectroscopy missions always going after the WIM, which is just looking out at blank patches of the sky and trying to find threads of stuff out there in the universe somewhere. Arcus will be able to do that. But the problem with that is twofold. One, it's really hard. Those filaments are very, very thin. And two, we don't have a whole lot of different models predicting where those, what those densities should be. There are a few, but they depend on a whole lot of parameters, and it's really hard to convince a review team that it is vitally important to understand how viscosity was implemented in this hydrocode, and that's why we're going to launch a $125 million mission. It is much easier and cleaner to point out that we can simply look at the radii outside of galaxies and clusters and understand better exactly what's going on at and beyond the virial radius, which is a region we all know that we're very much interested in. Arcus will be going after as well material in the true intergalactic medium, but this is a topic that is much easier to come to grips on and to show that there are at least multiple realistic models to compare against. We can also do local stuff. Every extragalactic sightline, conveniently enough, also goes through the Milky Way. And we're going to get the density, the temperature, mass distribution, shape. We're also going to do this for example, M31. We've got at least 6 sight lines that go through reasonably close to M31 towards reasonably bright AGN that we can get very nice measurements against. We also note here that if we can see gas in the local group, and the question is just how much of it is out there and what's the equivalent widths, it will have a quite different velocity than the Milky Way. Can we actually see that? For example, well, now let's just look here in our own halo of our galaxy. This is Arcus's resolution. Here's, for example, the XMM resolution. And here's the difference between a non-rotating hot halo and a co-rotating hot halo of our own galaxies. And you can see that we can very easily distinguish these two models. We can even tell the difference between just how much and possibly even where the gas might start changing its rotation curves. We can do other studies. It turns out, curiously enough, that AGN are not just good background sources. They are also interesting in and of themselves. So the problem has always been that, at least with X-rays, getting the really high resolution to compare with what the optical folks, for example, this is a Lyman alpha curve from HST STIS, have been showing, has been a real challenge. So here we're looking at gas presumably from narrow line regions, and we can see lots of different clumps here and what's going on in this image. Now we can compare this to, for example, LETG observations. This is 350 kiloseconds, and this is what you can do with the LETG. This is just hard. Now, yeah, you might be able to say there are some dips here, and so maybe there's some correspondence with this gas, but that's about all you can do. What can you do with Arcus? Here is the STIS curve in green, the same LETG points. Now the black points that you can see here in the red model are a model of what Arcus might be able to see that's based on the existing STIS and LETG data. And you can see that while we're not quite there at the full STIS resolution, we're certainly at least at the point where we can say, these two clumps match up and these two clumps do not. This is probably the same stuff. Something else is going on around in here. Hard to say what it is. We're not seeing any signs of, for example, this absorbing material, so something different is going on. This is the kind of data that we need in order to distinguish between, say, a clump that's interacting, that has Lyman alpha and doesn't have higher energy photons. This is sulfur 11 in this case, but we would have other choices as well. I just picked the sulfur lines. Stars. You can actually do quite a bit with stars. They're very nice point sources. They have a nicely bright spectrum. This is the Chandra HETG data in blue. This is half a megasecond of summed data. This is essentially everything we've taken on Capella over the years with Chandra. And this in black is the Arcus simulation of 5 kiloseconds. So this gives you an idea of just how much more powerful this mission is going to be, especially around this oxygen line. And what's so cool about this is you'll be able to very easily pull out all of these dielectronic recombination satellite lines. Now, this is one of those things that plasma spectroscopists usually pull out to impress the people who are not plasma spectroscopists. But with Astro H coming, we're all going to learn a lot more about these because they make fantastic diagnostics. And why is that? 2 reasons. One is their strength really depends only on 2 things: the temperature of the plasma, the temperature of the electrons, and 2, the number of ions that can be recombining and giving you those lines in the first place. So you've got something that doesn't depend, for example, on ratios of ionization balances and so on, is strongly indicative of non-equilibrium ionization versus equilibrium ionization, and gives you an independent temperature diagnostics that's actually quite sensitive. That you don't have to measure a Bremsstrahlung curve, you don't have to worry about all the different things that are going into a temperature diagnostic. This is one ion set giving you a very nice temperature and equilibrium diagnostic. This will allow us to, for example, determine the difference between coronal heating models that assume that the corona is being heated by some sort of constant wave motion, which would be essentially a gentle heating mechanism that is in equilibrium and keeps the gas in equilibrium at all time, and a nanoflare model, which is the other preferred model for these systems, where essentially all the heating is being done by sporadic impulsive heating processes, which are going to drive non-equilibrium processes at all times in the corona. This essentially is giving you either a constant equilibrium or something that should show fairly strong non-equilibrium effects. This is the kind of thing that dielectric recombination satellite lines are made for. So, what's this actually going to look like? The full focal length is about 5 meters. Now, fitting into the Dragon trunk, in order to get up there, you have to be about 1 meter long, which means we need to have an extendable optical bench here. But here at the front, we've got incoming light. We have 3 petals of silicon pore optics with gratings behind them. These are off-plane gratings being built by the University of Iowa. This is one of the 2 technologies that was under development for IXO, Star Tracker, Core Sun Sensor, all the other basic things. Then a data sending unit, which will send temperature data and so on down. Down here we have CCD type detectors. These are going to be made by MIT, along with detector readouts from Penn State. The entire body here in the pointing system is from Lockheed Martin. Let's see, Star Tracker would be from Germany. And the overall structure and integration and testing will be done here, with system integration and testing done down at NASA Goddard, because amongst other things, you need a chamber large enough to fit a 5-meter extendable optical bench. And those are a little bit hard to come by. Exactly what are these optics again? So here are the petals. It's designed this way because essentially we have to fit the entire thing into the space of about 1 meter cubed. So instead of having a typical round optic with a single focus, we instead have 3 petals, 3 pizza slices, thematically again, each of which will point down to a separate detector position and have a separate detector readout array at the base. So the SPO modules are all about the same area in physical size. They do increase in length as they get closer to the petal's tip down in here. And then beneath all this stuff, we have the grating structures themselves, and they're about the same size in point of fact. They're about yay big. So if you're interested, we actually have one of these. As part of the proposal for this, we hired Cosine to actually make us one of these silicon pore optics, and it's sitting over in a lab in CDP. I don't know where this instant, although it had better not gone very far because they're not cheap. But we've done some initial testing with them. They're looking very promising. What does the optical design look like? So this is a top view down, and here's a side view. So here we have the silicon pore optic, which is a series of stacked layers of silicon. Light comes in here, glances, hits an off-plane grating. Here's the off-plane grating itself. Now the trick to an off-plane grating is that it's got radially converging groove patterns. And it ends up scattering out of the plane of the array and gives you this nice arc here of dispersed light. We have a zero-order CCD and then 2 detector CCDs for each petal. So that's the way this will look. Here is the real problem with doing anything involving X-rays is you start off with 100% of all your photons. You lose 25% of them here. You lose another 25% of them here. The grating loses you another couple percent. Then you have filters which lose you some more. And you end up keeping as much as you possibly can. But it's a struggle every step of the way to keep your effective area up. Where do we stand on the grating, on the optics? The gratings themselves require arcsecond scale mirrors. And you might say, but arcsecond scale mirrors are hard to make. We've got an entire effort going on here to build arcsecond mirrors. We heard about them a couple of weeks ago, about how difficult these are. But the trick is, for a grating optic, we don't need an arcsecond point. We just need an arcsecond line. So we have one of those. This is a single silicon pore optics beam size, and you'll see it's basically an eye of Sauron. But in this axis, it's only about an arcsecond in width. So that's the direction that we choose to disperse along, and so we end up with a big, broad beam that we're selecting through, but we still get the arcseconds that we need. Where is it going to fit inside the ISS? Well, this is a Dragon trunk. Every time you hear of a SpaceX mission going up, this is where they put all the foodstuffs and all the stuff that needs to be in atmospheric pressure. And then they have what's called the trunk, and you can see we fit easily inside the trunk. Actually, you could fit 2 other missions the size of ours inside the trunk as well, although typically they often don't have anything up there. Where would we fit? This is actually one of the mounting brackets. This is literally where they keep spare parts for the station. Because if you have a problem for the station, you cannot get to a Home Depot quickly. So they keep a lot of spare parts lying around, but they have some spare facilities up there to hold them. That's one of the places where they do that. And I'll hit my conclusions and take questions. Thanks very much.
Thank you, Randall. We have time for questions.
Are you going to survey a certain region of sky, or do you have a list of?
We have a list of targets. They're all point sources. It is likely that we'd be able to observe some slightly diffuse sources, but we've never actually done the simulations because we had our hands still just doing the point sources. Our plan is to do a fairly deep survey of AGN for the structure formation work. That's about 10 megaseconds worth of time. And then a collection of stars. We have an exoplanet observation in there looking at a transit. We've got a series of AGN that we're looking at with warm absorbers and similar systems, and a collection of other sources in there. I forget all the exact numbers right this instant.
Ramesh, you have a question?
Yeah. I haven't heard of the silicon pore optics.
Mm-hmm.
Could you say a little bit more how it works?
Certainly. So here's as good a picture as any. This was an idea that actually came about 15 years ago, I think. And the idea is that you use a lot of the same technology that's being developed for the electronics industry. So you get very high-end, very pure silicon crystals. You then slice the crystals into 12-inch flats, dice them into squares like this, and then mechanically you groove them this way. And then you wash them to the nth degree to get all the grit out of them. What you have now is one surface, which is essentially a perfect mirror. It's a perfect crystal. You can coat that, and they do, with a combination of gold and boron and carbon. So it's a boron, carbon, and then a gold on top of that, I believe. Then you lay that on top of a mandrel and form it down to the right shape. And then you take another one and you do exactly the same thing. What you end up with is a series of small pores, thus the name, silicon pore optics.
So these are really holes.
They're really holes that just go all the way through. The interesting thing about this is they use no glue whatsoever. The entire bonding process works by atomic force. Just basically you have pure silicon on pure silicon and it reattaches itself and holds on to itself. They have been making these now in the Netherlands for at least 15 years, getting better and better as they go along. They really have not been focusing on making optics for the X-ray grating world. They've been trying to make them to get the overall PSF down smaller. But basically a side effect of the way that you make these and the way the physics works is you always get a PSF that looks like this. So it works beautifully for us.
Yes.
In terms of the energy range,
Yeah.
what would be the limit as for just the optics, not the gradients?
The optics will work essentially. The Athena mission will go up to 12 keV. There's no reason that the optics won't work up to a much higher energy. The problem is that the gratings themselves simply basically stop working at around 1.5 keV.
Okay, yes.
I missed, what is the field of view?
It's primarily a point source mission. The actual field of view is about, of the detectors, is anything with photon light within about 10 arc minutes will show up, but it's not really an imaging, so it would just diffract along it.
I was thinking of confusion.
Right. But it would end up in a different part of the spectrum with a different part. Essentially, the confusion would be dealt with the same way we deal with confusion in Chandra, HETG, for example.
Okay, last question.
The reflection grating is on the RGS.
Mm-hmm.
Had a rather unfortunate scattering properties that led to a rather broad base of the line spread function. Is that something that's been dealt with in the intervening time?
Those were not off-plane reflection gratings. Those were in-plane reflection gratings, and these are the off-plane ones. The measurements that we have here that Randy McIntyre at Iowa has done don't show. I mean, they're not perfect Gaussians throughout, but they don't nearly have the wings that you're used to in the RGS. So yeah, they're much narrower. We don't have that problem.
Okay, thank you very much.